on YouTube. Okay. All right, here we go. All right, so this is lab 3. Was it February 4th? Okay, lab 3, Thursday's lab. Okay, so on the pre-lab, I want to talk about cardiac output, stroke volume, and heart rate. The interesting thing here is that cardiac output basically is how we measure how well the heart is moving blood, okay, circulation. And there's two components that will help us calculate cardiac output. And that's cardiac output equals stroke volume times heart rate. And we're going to play off these, and I'm going to try to explain how we do this. Heart rate is self-explanatory. It's the amount of beats per minute. All right. Stroke volume is the volume used, or the volume that the heart ejects out. It's measured in mils. We're going to talk about ejection fraction, which is the same definition of stroke volume, but it's a percentage. Okay. That is usually a test question or quiz question that shows up. What's the stroke volume? If you answer 40%, then you just gave the ejection fraction. All right, stroke volume is measured in mils. So it's going to be about 35 mils, 40 mils. It's not 35% or 45%. You just got suckered. Ejection fraction is the percent. All right, we'll touch down on that further down the lab. Okay, so let's see. Let's go down to the bottom of the pre-lab and briefly touch on systole and diastole. Now, we kind of hit on these last week, and you guys answered them, but I want to revisit these vocabulary words. Systole basically is just the contraction of the heart, right? Let's see. And let me get this chat up in case you guys chat something. I'm going to try to walk around here a little bit. Systole is the contraction part of the heart. Diastole is the filling phase of the heart. Excuse me, when I talk about filling phase, I'm talking about blood coming into the ventricles or blood coming into the atria, because we have to get blood in the heart before we contract it, right? So that's the diastole part. I think diastole, actually, it makes up 2/3 of the whole heart cycle. You know, like this love-dub. Diastole will consume 2/3 of that cycle, and then systole so fast it's 1/3 of that millisecond, I guess. Okay. On page 29, I want to talk about some more vocabulary. I'm going to introduce at the very top when you see end filling volume and end ejection volume, those are the same thing. Well, let's start with the first one. EFV, that's end filling volume. I'm going to use end diastolic volume, which is EDV. That's the more proper term. The other one's more elementary. EDV, or end diastolic volume, let's break it down. This is the volume in the heart at the end of diastole. Or this is the filling stage. If my microphone just cut out, my bad. So end diastolic volume or end filling volume, that's the volume after we have the filling phase or the diastole stage. And the other one is end ejection volume. The end ejection volume, that is, believe it or not, we have residual blood left over after our systole, after we contract the heart. We don't push everything out. We still have some residual blood left over after the ejection fraction or stroke volume. So that's going to be called end systolic volume. Those are the words I'm going to use. So you may see these words on a quiz or an exam, and the point is that I don't want you to get confused, because end filling volume is the same thing as end diastolic volume. End end ejection volume is the same as end systolic volume. We're okay on all that? Okay. All right, so we talked about stroke volume. Now, stroke volume, basically what I said is the amount of volumes or mils ejected from the heart after systole. So this is the first question I got hung up on Tuesday. We had to work it out all together, believe it or not. In figure 3, the volume in the metering tube before 0 mils and after 60 seconds is 200 mils of pumping are shown. So at 0 seconds, we have no mils. After 60 seconds, we have 200 mils. And this is kind of like showing these graduated cylinders if we were to do like a quick experiment. What that pretty much is detailing, that is the cardiac output. Because cardiac output is the amount of mils over minutes. Okay, so the question says, if there are 10 pumping cycles, that's heartbeats, in 60 seconds, what is stroke volume? Well, how we would manipulate that, do you remember that first equation I showed you all? Let me find a pen. Whereas cardiac output equals stroke volume times heart rate. We're going to solve for stroke volume. So if you remember your algebra skills, I don't know if you guys can see that. Use black. So if you've done the math right, you should have stroke volume is equal to cardiac output over heart rate. Okay. Stroke volume is equal to cardiac output over heart rate. That's how we solve. So you're going to have to be able to manipulate this equation on the exam or on the quiz, okay? If they ask you, if they give you cardiac output and they give you heart rate, what's the stroke volume? You have to move it, manipulate it around so you could get stroke volume. Same with heart rate. And then, of course, cardiac output is going to be what you should have memorized. Does that make sense? Are we okay on that? Okay. Brushing off some math. All right, so back to the question. If you have 200 mils, so it's going to be 200 mils, which is your cardiac output, divided by your heart rate, which is 10 beats. It's going to be a stroke volume of 20 mils per beat. All right, so the end diastolic volume is the amount of fluid in the diaphragm ventricle immediately before it was compressed. The volume left inside the diaphragm after ejection or stroke volume is called the end systolic volume. We've kind of already talked about that. That's just a fancy way of saying that's what's left. That is what's left. That's the amount of volume that's left after we eject the blood out of systole. Okay, end systolic volume. So if we have an end diastolic volume, that's the amount of blood about ready to get ejected out, at the end of diastole, that's 100 mils. And then at the end of systolic volume, we have 60 mils. So what was the stroke volume? Well, we're going to take 100 minus 60. That's what's left over. That's going to be 40 mils. That's another way of calculating stroke volume. The easier way, in my opinion. Yeah. So at the end of diastole, I'm all filled up with blood, right? All of a sudden, if I'm the heart, and at the end of diastole, we spent all this time filling me up with blood, and then all of a sudden, that's at end diastolic volume. So we're plumb full, 100 mils. If I contract, I just pushed out a bunch of blood. It's systole. At the end of systole, I have some residual blood left over. In this case, it's 60 mils. How many mils was pushed out of me? 40 mils, or that's the stroke volume. Does that make sense? All right, you kind of have to think about it. You should have seen me thinking about it on Tuesday. It snuck up on me pretty hard. Especially that 10 pumping cycles. I thought that was ejection fraction. No, it all way off. I'm talking that's the average stroke volume. All right, now here's the part. Ejection fraction at the very bottom. This is the test that cardiologists will use to determine what's your heart health. If you have a failing heart or you are in some stage of heart failure, this will tell you what stage you are in, your ejection fraction. Excuse me, normal ejection fractions can be anywhere from 60% to 40%. My grandfather at 89 years of age, he had heart failure. I think last few months of his life, he had an ejection fraction of like 14, 13%. So it's a huge range. You know, you can live with heart failure for a long period of time. However, your quality of life is probably not the best, because if you've ever been around somebody with heart failure, you probably recognize they're just breathing like they're out of breath all the time, because they have to compensate the amount of oxygen to move to the organs, to the brain. And you know, they could probably walk, but they can't. You know, there's no rigorous stair climbing or anything like that, because the ejection fraction, that is the amount of blood that is leaving the heart after every contraction. If you're used to moving 60% of your blood, and all of a sudden you're down to 15% of your blood, you're not leaving a lot of blood at all. So how the body compensates for that is that you would sit there and almost, I don't want to say hyperventilate, but your respiratory rate is certainly elevated, because you have to take in so much oxygen to keep up the oxygen stores in your body. Okay, so ejection fraction, that is end systolic volume divided by end diastolic volume. It's written in the lab. I'm going to give it here. Ejection fraction is equal to stroke volume divided by end diastolic volume. And see, here's the percentage part. I might have to buy some of these or something. Yes, that's right, Grace. 40%. It is 40 divided by 100, which is 0.4, multiplied by 100. That's the percentage part. Gives you 40%. For you guys that didn't hear online, that's going to be 40% at the very bottom of 29. The ejection fraction is going to be 40 divided by 100 times 100, because it's a percentage, is going to give you 40%. Okay. All right, so do we want to demonstrate the pumps, or do you want me to kind of tell you what to expect and then we can work through it together? It's up to you guys. You want to do both? Okay. So what we can, and you guys online, you're just going to hang out, and I'm going to come back and tell you the important parts, but we're going to try to walk the pumps. We'll expedite it a little bit. Huh? No, that's fine. I'm not worried about it. It'll be fine. This is to demonstrate stroke volume and all that. The concept will be what we just went over up here. This will be the big stuff. All right, so this one's got blood water. I'm not getting my mask up. It's drained. This is the valve. So when that drains, what we're going to do, we're going to do this couple pumping cycles. And you may get so the most effective way to carry out the activities in this lab is for each member of your group to have clearly identified roles. All right, well, since we got an abbreviated class today, we're all going to kind of do this together. So you're going to have a reader, an information gatherer, an instrument operator. We'll be okay. All right, so each of those valves I just touched, I think everybody's is closed. If you want to do this, great. If you don't, you can listen to me and I'll kind of explain what we're going to do. Okay, we just emptied the meter. We did that. Now squeeze the pumping bulb until it totally flows and keep it squeezed. All right, so if you were to squeeze this pump, you all see them around there. If you want to do it, go for it. How much fluid is in one squeeze? Everybody's going to be a little bit different. One squeeze. So I have 26 mils. I don't think that was really good. You guys here probably have. Now make sure your valve is closed. Your valve may be open. That may be why it didn't stay. Yeah. Okay. So now for number 3, I'm going to pretend that I got 26 mils. All right. So what would be the volume ejected from the heart be called? Yes, that's right. 1 pump of blood is equal to the stroke volume. Okay. Protocol 1, page 31. All right, I'm on page 31. Beginning with your first pump at 5 seconds past the top of the minute, how many cycles will be completed in 1 minute? So I did the math already for you. If you squeeze your bulb every 5 seconds for 1 minute. Yeah, go ahead. Oh, I'm on top 31. I'm top 31. I just started. I'm on number 4. Beginning with your first pump at 5 seconds past, how many cycles will be completed in 1 minute? Well, we're going to complete 12 heartbeats, right? For every 5 seconds, for 60 seconds, it's going to be 12, a heart rate of 12. All right, so if you were to squeeze it, so number 5 asks us, what is the pumping rate? And, well, it's 12 beats per minute, okay? So pump every 5 seconds and then complete the table. So right now, how many mils do we have in there? Grace, how many pumps did you do? Did you sound really good pump? You seem like you got a lot. 10 mils? Yeah.
Like 40.
40? Was that 1 pump? Okay. All right. You guys probably have something around 4, 5, 6, 5. No, keep it in there. Yours will just be a little bit more than everybody else's. So all of a sudden we have right there in the trial 1 meter tube volume. Well, this is 4 mils. Let's say 4 mils. Excuse me. Let's keep it on track here so I don't embarrass myself with my math. This is your residual volume. Okay. Remember what I told you about the residual volume? If you were to pump blood, some of it kind of kicks back. This is what comes left over. It's not a big deal. It's just something you need to keep in mind. So after a pumping cycle, we can write this down, and you can use my numbers if you want. You don't have to sit here and pump it 12 times. The first trial is going to be like this, and then we're going to use these numbers throughout. So after the first pump, we got 18 mils, okay? This is under the meter tube volume part. So we're going to do 18, and the next time we got 30. Trial 3, we got 44. Trial 4, we had 54. Trial 5, we got 65. Trial 6 is 78. Trial 7 is 90. Trial 8 is 102. Trial 9 is 112. Trial 10 is 122. And then 140. And then the last one is 154. Okay. So that residual volume I told you guys was 4 mils, right? The first time we pumped it, I told you we had 18 mils. Our stroke volume is going to be 18 minus 4. So 14. That's under stroke volume trial 1. We cool? All right. You just holler if you kind of get confused or you're a little behind. We'll try to keep everybody together. So, and I'm gonna let you guys do this on your own. So that's the first example. Now, trial 2, under meter tube volume, I said we have 30 mils, right? Take the 30 minus the 18. That's going to give you the stroke volume on trial 2. So 30 minus 18 is 12. That's your stroke volume for number 2. Okay. 44 minus 30, 14. That's for number 3. Are we okay? We're following? All right, I guess so. Yeah, just subtract it. 54 minus 44, that's 10 for number 4. 65 minus 54, that's 11. 13. So let me know when you're done. I'm sorry, Samantha, I just saw your chat. What was the answer we came to on number 5? That was for the meter tube volume was 65. Well, the meter tube volume was 65. No, I'm answering I left somebody behind on the line here. She had a question. No, the stroke volume for number 5 would be 11. $65 minus 54. That's 11. And let me know when you have that table filled out. If you get hung up, just let me know and I'll tell you where we're at. And we'll answer number 9. Well, we can do it together. I just want to wait for everybody to get the chart filled out, and then once everybody's caught up, we'll do number 9. So are we okay? I don't want to rush anybody. So if we want to go over the answer on stroke volume real quick, it should be 14, 12, 14, 10, 11. Trial 6 is 13, 12, 12, 10, 10, 18, and 14 for trial 12. All right, so we good? Okay. Number 9, determine the average stroke volume. Well, for each of those different stages, we found the stroke volume. All right. So if you add all those up, I believe you get somewhere close to 150. And then you divide that by 12, because that's the amount of times we did it. That's an average we're talking about. So it should be 12.5 milliliters per beat. Number 10, determine cardiac output by reading the total volume collected in the metering tube. Volume in pumping cycle 12 minus the 4 residual. That's what we started with. So at number 12, I told you that we had 154 under the meter tube volume, right? Subtract your residual volume from that, which we started with 4 mils. Some of you all had 4 mils in your graduated cylinders. So what is that? It's 40 mils per minute. That's cardiac output. Cardiac output is the amount of mils that the heart can throw out into circulation over 1 minute. All right, so table 1. If we were to do this 2 more times, okay, this whole chart 2 more times, then you would still keep your heart rate around 12, but then your cardiac output would be, let's say we do, the first time we do 150, and then trial 2 would be 152, and then the average of those would be 151, right? 150 plus 152 divided by 2, the average, if you take the middle, 151. That is mils per minute. The stroke volume for trial 1, table 1, if you follow the equation, would still be 12.5. And then trial 2 would be 12.7. And then obviously we take the stroke volume average of those two, which is right in the middle, 12.6. So are we cool on all that? Well, sorry, Samantha, I just saw your chat. What part? 140? I think it's 150. I don't think I remember seeing it. It'd be 150. If you're trying to answer number 9, it'd be 150 divided by 12. That's 12.5 mils per beat. Okay. Um, 154 minus 4, because that's the residual. The 4 milliliters is the residual volume that we had in the heart. So we have to subtract that out, and it gives you 150 even. And then we would take the 150 divided by 12, that's number 9. That'd be our average stroke volume over those 12 trials. Okay, so calculate stroke volume. In the lab, it says stroke volume is equal to cardiac output divided by heart rate. We have that written up here. So what is it? Well, it's 12.5 mils per beat. We've kind of already determined that. And at the end of this lab, I'm going to try to bring all this together. And I want to explain to you what happens when we increase certain parts and how the heart will compensate. What happens when you exercise? What happens when we do enter heart failure? All right, now, are we okay on page 31? Is there any questions? Let me know. It's not a big deal if I got a little ahead of you. Okay. 32, page 32. So we're not going to do all that again. That's just to demonstrate it. Beginning with your first pump at 2 seconds past the top of the minute, how many cycles have you completed in 1 minute? Well, if we're going to do every 2 seconds for a minute, 60 seconds, so it's actually going to be 30 times, 30 heartbeat. 30 times per minute, so that's going to be our new heart rate. Okay, that's the answer to number 1. If you do it every 2 seconds for 1 minute, you do it 30 times. Cool. What is the pumping rate? 30 beats per minute. Compare this heart rate to the heart rate in protocol 1. Based on the comparison, what would you expect cardiac output to be? All right, so think about that. We just upped the heart rate from 12 to 30. What do you expect the heart rate, or the cardiac output to be? Huh? Yeah, you got it. All right, this is like if you're exercising, right? Actually, it'd be a lot more than that, but let's just keep it for lab purposes. It'd be 320 mils per minute. That's number 3. All right, so it says empty the metering tube and operate the pump as before, only this time every 2 seconds for 30 seconds. Okay. We don't have to do this. That's okay with you guys. Now, what was the cardiac output? It ended up being 332, which is right there at 320 earlier. You can calculate the average stroke volume. So let's go down to table 2 down here. And for the trial 1, we found the cardiac output to be 332. Using this equation up here, the stroke volume was 11. And then for trial 2, the cardiac output ended up being 318. And the stroke volume was 10.6. All right, so now we take the average of those on that one. So 332 plus 318 divided by 2 is going to give you 325. And then the average stroke volume between 11 and 10.6 is 10.8. So let's compare table 1 on page 31 and compare to table 2 on page 32. So what do we notice? We upped the heart rate, right? We upped the heart rate. We found out that cardiac output increased substantially. What was it, around 100 something, what we say it was? 150 to around 330-ish. All right, so we more than doubled the cardiac output because we increased the heart rate. Did you notice something about stroke volume? Went down. Does anybody know why? Just think about that. Think about that. If you've increased your heart rate, so instead of doing love dub, love dub, love dub, you're doing love dub, love dub, love dub, love dub, love dub. We're increasing the heart rate. Stroke volume is the amount of blood ejected from the heart after systole. But our stroke volume just went down. The heart does not have the same amount of time it would at resting heart rate. Okay? So if we're having, this guy goes back to the EKG, honestly. If you have adequate time for the blood to go down in the ventricle, then we're going to have a higher stroke volume, right? Because things are slower. The heart rate is slower. It gives time for blood to come into the heart, fill up, get squeezed out. We measure stroke volume. If the heart is beating fast, then we don't have a lot of time for that blood to enter the ventricle. Therefore, we have a lower stroke volume. We cool on that? Think about it. So if we have a lower stroke volume because the heart rate's beating so fast, then that's why the heart has to compensate for a higher heart rate to keep that blood, that oxygen demand where it needs to be. Yeah? No? Are we getting it or are we not? I see blank looks. How about you guys online? Anybody follow that? We're starting to manipulate things. Chat me something, let me know. 320, that is when we look at, I think we just took it from right here. Heart stroke volume, SV. This would be, what did we say it was, compare? Yes, I think so. I think times 30, that one should be around 320. I think I did this last night. Yeah, compare the heart rates of on one. What would you expect? 320 mils per minute. Yeah. When you see mils per minute, you're talking about cardiac output. So I said earlier that the average, I said that the cardiac output is now increased in table 2. That has decreased our stroke volume. That's a take-home message for this lab. If you increase the cardiac output, or you increase the heart rate, your stroke volume is going to go down. It's an inverse relationship. One goes up and the other one goes down. That's kind of important. Hold on, Samantha, I'll get to your point. Do you guys understand that? Yeah? Okay. If you don't, I'll just say it again. It's okay. You have to get a couple passes at this. I will. Let me get to the stroke volume is lower just because it doesn't have the time to relax and release as much blood as when you are at rest. Yeah, that's right, Samantha. You hit it. So if the heart rate goes down, the stroke volume goes up. Yes, you're correct. So what Samantha said online was that basically when the heart rate is slowed down, it has enough time, the heart has enough time to fill up, okay? And when it fills up, it's able to eject out a larger stroke volume, okay? That's like a heart rate of what, 12, what we said? Because at a heart rate of 12, we said the stroke volume was like 12 or 13 mils, right? Yeah, 12 and a half, 13 mils of stroke volume at a heart rate of 12 beats per minute. Now we've upped our heart rate to 30 beats per minute. We just saw on table 2 that our stroke volume decreased to 11 or 10 and a half. That's because the heart does not have the same amount of time to fill up and eject as it did at 12 beats per minute. So you have to think about this. This is kind of what happens when you exercise. Eventually your heart will get really good and it'll contract a lot harder. That's called an entropic, a positive entropic function, and it'll contract harder to push out that blood to meet the metabolic demands of your muscles. Okay, so increase in cardiac output will decrease stroke volume. I want to move on to protocol 3 here on page 33. Excuse me. Protect the cardiac output you will achieve by pumping as fast as possible. So if we were to pump this thing as fast as possible, it has to exceed over 160 beats per minute. Let's say we did 180 beats per minute. So what would we think would happen? Well, yes, the cardiac output would increase and the stroke volume would decrease. Is that what she said? Okay. So your cardiac output would increase. This is what happens when you exercise. That's what I'm going to do tonight. And do something I feel tense. Elliptical. Elliptical for me, yeah. Certainly elliptical. I don't have knees like I used to. Yeah, cardiac output would increase because you were exercising. If you do a vigorous exercise, you will find that your heart rate will probably jump up to 100 beats per minute, sometimes 200 beats, sometimes 210. If you got some really good cocaine or you got some good upper, you can hit 22, 230, 220 beats per minute. Yeah. What'd you say? Yeah, exactly. 200. Yeah, I mean that's vigorous. I think on the lift pull, if I'm stroking it hard, I'm like 180ish, 190ish. So you try to want to get it down as much as possible while still maintaining your exercise. But yeah, so it's always good to check your heart rate. So repeat the experiment in protocol 2 above, but this time pump as rapidly as you can for 30 seconds. Keep track of the numbers that you pump. Again, double your volume so the data may be expressed in mils per minute. All right, so we're going to do this in table 3. And it says repeat the experiment one more time and record your data in table 3. Then calculate stroke volume for each trial. And finally, compute the average heart rate, cardiac output, and stroke volume. Okay, so let's say we did this, right? And we squeezed this bulb over 160 times per minute. So our heart rate, let's say for the first time, we did 204 beats per minute. We squeezed that thing 200 times. For trial 2, heart rate, we did 192. And then the average, if you average 204 and 192, we get an average of 198. Okay. Yeah. So cardiac output is 56 milliliters per minute, 52 milliliters per minute, and the average of those two is 54. It's way off from where we were in trial 2 or protocol 2. Stroke volume. Stroke volume is even lesser than that. 3.6, 3.7, and 3.65 mils per minute. For cardiac output, per minute. Do a slash there. Yeah. Mils over minutes is what it should be. And we say that as mils per minute. All right, so we filled out table 3, right? Everybody fill out table 3. We repeat some of those numbers. Now let's not move off that graph. I don't want to do the graph yet. Let's talk about this. We had a heart rate of 200 beats per minute. That's a lot. All right, you just ran a sprint, right? Maybe you just ran a big sprint. We said our cardiac output is down to 56 or an average of 54 mils per minute. Our stroke volume dropped dramatically down to 3.5. Why is that? Well, it's kind of what I built on before. Now we're pumping the heart so fast, it has little to no time to fill up. And then our stroke volume is down to 3.5, a little over 3.5. So even though the body compensates for a high heart rate, it can only compensate so much until it starts to decrease and then just fall off the graph. And that's what we're going to do next. So once you surpass 160 mils, when the heart is beating between one beat and the next, the ventricle fills with blood. But once you pass 160 beats per minute, you're beating so fast, it's hardly any time for the ventricles to fill. Because of the decrease in ventricle filling and the heart rate increases so much, the stroke volume decreases in this, and therefore it decreases the filling time. At first it does it, let's see, let me read this. I scribbled this down so fast last night. So when we increase the heart rate, it will decrease the stroke volume. We know that part. We've solidified that. But once we pass 160 beats per minute, the stroke volume drops so much that you can see our cardiac output has a dramatic drop. All right, so do we get that? Do we understand that? It's all about stroke volume and cardiac output. And the only thing we're changing here, the only thing we're changing is heart rate. No, you're going good. Oh, no, you had it. Don't change. You had it. Over 60, if we're at 160 beats per minute, your cardiac output will just drop off because your stroke volume's dropped off. Yeah, I think, but there's a lot of different factors we're not taking in consideration. If you want to go on, like, if you want to talk about what contraction is and what calcium's role is in, and like if somebody codes, right? They bring the paddles in, like we talked about with the EKG. They're also going to give you an injection of calcium. Calcium will bind to the heart, the cardiac muscles, and cause a strong contraction. You know, all of a sudden, this strong contraction is called an entropic effect, a positive entropic effect. And what happens is they stick a needle, or they give you an IV, or they may just stick you right in the heart and give you, or epinephrine's another one they'll give you, calcium epinephrine. And what that does is that it will cause a strong contraction. If you cause a strong contraction, what's that doing? Well, it's your stroke volume, right? You just contracted this muscle so hard that your stroke volume just went sky high. That's what ejected out of the heart. So there's other factors to consider here. This is just kind of like what happens in if we just consider these. So at 60 beats, heart rate goes up, cardiac decreases, and stroke volume also good. That's right, Andrea. That's right. It always helps everybody else, especially when you can read your colleagues' chat comments. And I think you'll be able, once you read it instead of listening to me, it certainly does help learn the material. Okay, so we kind of get that, right? Let's go down this graph. We're gonna let's see, table 4. Let's go over 34 real quick. We're gonna look over table. I think we've already talked about table 4. Explain in your own words how increasing heart rate affects cardiac output. Well, if we increase heart rate, we're going to decrease cardiac output. Explain the relationship between heart rate and stroke volume. If we increase heart rate, then we decrease stroke volume. I've kind of already mentioned that. Think about that. If we're contracting the heart so fast, it doesn't have time to fill up. It doesn't have time to fill up, and the stroke volume is going to be lower than what it would be if you're, watching TV at a lower heart rate. What other changes beside heart rate would increase cardiac output? Well, if we just so happen to take a shot of epinephrine or calcium, or we have a bunch of caffeine, and we increase our stroke volume, would also increase our cardiac output. All right. So Samantha, you said, so cardiac output and stroke volume have the same reaction to heart rate. It's more like opposite. Heart rate's going to be the one that we changed a lot. So heart rate's going to change cardiac output and stroke volume. Heart rate will change stroke volume, and then subsequently stroke volume will change cardiac output, because you got to think about the equation. Cardiac output equals stroke volume times heart rate. So in our bodies, if I'm walking up the stairs, my heart rate's going to jump up a little bit. My stroke volume is going to go down just a tad, which will affect my cardiac output. Hope that answers your question there. Okay, so this graph on 35. When we're talking about stroke volume, at 12 beats per minute, down there on the x-axis is our beats per minute. Okay, we got 12, and we have 30, and then we have really fast, right? So if you think about it, at 12 beats per minute, our stroke volume was kind of high, right? Because the heart was having enough time to fill up with blood. We'll start up here, way up here. As we go to 30 beats per minute, it kind of went down, right? This is right around 30, because now we've increased the heart rate. And then it went really fast, right? What happened? Well, it plummeted. Went way down. All right. This is all can be seen in the tables. Table 1, 2, and 3. For you guys online, I'm going to kind of bring my computer over here and show you what the graph would look like. So this is my makeshift graph for stroke volume. If we had, this is like, okay, if we had 12 beats, it'd be way up here with the stroke volume. As we increased the heart rate, our stroke volume went down, and then it dropped considerably when we went really fast. And that's stroke volume. That's because the heart does not have enough time to fill up, and then it can only compensate so much, and then it just falls off. So, cardiac output. Cardiac output will look something like this. At 12 beats per minute, we were kind of like right here, and then we went up at 30 beats per minute, because really what's driving cardiac output at that point is heart rate, if you think about it. Because if we increase the beats per minute, we go up to 30 beats per minute, it's way up here. This is cardiac output. And then all of a sudden, when we go really fast with the heart rate, the heart cannot compensate anymore, and it goes down like this. So as heart rate increases, cardiac output increases, despite the stroke volume decreasing. All right. So yes, stroke volume does drop off, but heart rate really is what garners the heart's function. All right, so this is our heart rate right here. Let's see if I can get this on here. So this is where we started at 12 beats per minute. We went up in table 2. You could see our cardiac output jumped to 330-ish or something like that. And then as we went really fast with our heart rate, it just plummeted down. Okay? And that's because as heart rate increases, cardiac output increases, despite stroke volume decreasing. But once we pass a high heart rate level, which was 160 or 180, the stroke volume decreases rapidly. Okay. So that's the lab. It's a lot, isn't it? That's the big take home right there, is to be able to manipulate that equation right there. If it asks you for stroke volume, if it asks you for heart rate, if it asks you for cardiac output. Ejection fraction, don't forget about that. Ejection fraction is a percentage. That's also an equation on there too.
It's the same as the percent.
It's the percent. It's the stroke volume percent. Yep. So is there any questions? If you boil it down to the nitty-gritty stuff, it's really not that complicated. We took a roundabout way of doing it, of working through the lab. I think if you were to join the spotlight session in 139 and have Dr. Sharp or Mr. Davis explain this to you in their manner, then it'll help. Rewatching this on YouTube would probably help, or just rewriting it and understanding what happens when you exercise, what happens when you manipulate heart rate, how your heart will adjust to it. Is there any questions? All right. Well, I'll drop them. I'll open up the stopcock and drain them. Okay. Well, that's all I got. Do your quiz tonight if you haven't done it already. I have to go in there and manually grade them again. I don't think they'll be. It won't be like last time where I had to go in there and do some heavy lifting. So other than that, I'm okay. You guys can head out if you want. No problem. See you next week. All right, you guys online, are we okay? All right, thank you, Samantha. All righty. You let me know. Thank you, Andrea. Have a good day. What's up?